chapter 18, I think, 17, one of those. I think it's 17. We were talking about electrochemistry, and we talked a little bit about sort of the relationship between E of the cell and some of our thermodynamic sort of properties. We saw this equation earlier. Our delta G is equal to minus NFE. That is our Gibbs free energy is equal to N, which is our moles of electrons, F, which is Faraday's constant, and E is our E of the cell. And what we saw is we talked about sort of the relationship between E of the cell and delta G. If you have a positive voltage, that would result in a negative delta G, which should be a spontaneous reaction. If you have a negative voltage, the negative there plus the negative there will turn that delta G into a positive value, which means it will be a non-spontaneous process that will occur. We also saw sort of the relationship that goes with our equilibrium constant as well, which is this guy. And these are our same sort of guys. This is our gas constant, which is our 8.314. But our equilibrium constant obviously does relate with our other values here. So again, if we look at our K with our delta G and our E, if we have a positive E, it should give us a negative delta G, which means it is going to be spontaneous. Spontaneous means we should have products. Products means we should have a larger value of K in that case. Opposite would be true if we have a negative value for E, once again, giving us a positive value for delta G, meaning that this would be non-spontaneous, which means really reactants are favored here. And that would give us a smaller value for K. So again, all those guys should really agree with each other when you kind of go through your calculation. At the end, we talked about what happens sort of under non-standard conditions, which is known as the Nearst equation. And the Nearst equation is used when, again, something is not under those standard conditions. So a reminder, as we talked about standard conditions, 1 atmosphere for pressures, 1 molar for your solutions, and usually a temperature that's like 25 degrees Celsius. So if you do sort of become under those non-standard conditions, you can use the Nearst equation to see how the cell voltage would be affected by that. Our E naught here would be our cathode minus our anode. The rest of these guys would obviously be the normal things, our 8.314, our temperature in Kelvin, our Faraday's constant, which is 96,500. And again, our Q here, remember Q is our reaction quotient, which is our products divided by reactants. And once again, obviously taking our coefficients into account when we do that. As we also talked about, this equation here to the right is really, from this equation. But these two are really tied to each other. Again, if we do get to at equilibrium, E would equal 0. And again, Q would equal K, which means this equation here becomes this equation here. And they're basically how we get to both of those equations. Any questions on any of that stuff there we talked about? We also talked about, as we did before, again, if you do change the sign for the anode when you're doing the E of the cell, remember you do want to add those values together. And if you decide not to change the sign for the anode, then you should subtract the two values when you calculate E of the cell. Any questions on any of that there? Okay, and again, on the bottom here are the same sort of reductions of that equation. If you are at 25 degrees Celsius, kind of the R, the T, and the F become kind of a constant value at that point. Again, you don't have to remember those. You can just obviously remember the one in the box and just put the values in, and you get sort of the same answer. So let's take a look at one here. Will the following reaction occur spontaneously at 25 degrees Celsius? if we have a concentration for iron to 0.6 and for cadmium 0.01. There's some of the SRP values given to you here. It'll take 3 minutes to see what you come up with. Okay, let's take a look and see how you're doing. So in this particular case, we want to know if it's going to be spontaneous. We do have some concentrations given to us. The first thing we should note is these concentrations are not 1 molar, which means they are not under standard conditions. So that then should direct us to the Nearst equation there that we just saw, which is E is equal to E naught minus an RT NF natural log of Q in this case. So we do want to calculate E of the cell, as we do need to do that. So we want to do our cathode minus our anode. And in this case, our cathode is the iron, and we want to make sure that we do look at it. I know it was given to you in your notes, but just in case it wasn't given to you in your notes, remember that the iron is +2 going to 0 in this case, which means it is going through reduction, while the cadmium is 0, ending at +2, becoming more positive. So it's going through oxidation. So once again, as we talked about a number of times last time, you do need to look at the actual reaction if it's given to you and determine who's being oxidized and who's being reduced to correctly identify your anode and your cathode. Again, if you are not given the equation or any information about how it's occurring, that is when we roll with the more positive one is our cathode. But again, if you are given it like here, we do need to look at it. So in this case, I'm just going to subtract. So I'm not going to change any signs. So E of the cathode minus E of the anode. So our cathode, once again, here's the iron, which would be minus 0.44 volts minus a minus 0.4 volts, going to get us a number. Going to give us minus 0.04 volts here. Now, under standard conditions, is this reaction spontaneous? It is not. We have a negative E, right, which would give us a positive G. So under standard conditions here, this reaction would not be spontaneous. So what we're trying to see is by playing with the concentrations here, will this reaction maybe become spontaneous by playing with those concentrations? That also is going to require us to calculate Q here along the way. So Q would be our product, which in this case would be our cadmium, divided by our reactant, which would be our iron. Obviously, the solids like normal would not be included, which is why you have no numbers for those guys. That would get you 0.01. Logical answer there, why you have no numbers. There you go. 0.6 molar there. And we'll do 0.01 divided by 0.6. Going to give us a 0.01666666. Keep going. At this point, we have pretty much everything else we need. Obviously, this needs to be converted to Kelvin. So that's going to be a plus 273, which will give us a 298 Kelvin. And R and F are constants that we have. So R, again, is our gas constant. And F is Faraday's constant, which I think we've been using the rounded number here of 96,500 joules per volt per mole. All right, so I think we got everything we need. We're just going to put it in. So E is going to equal minus 0.04 volts minus our 8.314. Our 298 divided by, I guess the other thing we should figure out is N. N in this case is, yeah, N is, you don't add them together, but it is just 2 electrons in this case. I think you have the half reactions there on your paper. So the cadmium there is going to lose 2 electrons. The iron is going to gain 2 electrons. Remember, you don't add both of those together. It's just the electrons that are being transferred from the anode to the cathode, which in this case is only a grand total of 2. So Again, you would not want to use 4 here. Yeah. Say it one more time. The charge of. It would, if you wanted to add them together. In this case, I'm just subtracting. So I'm going to, that's what this will change the sign for me, remember? Yeah. Yeah. Yeah, so I believe you have the reactions there, which is in this case here, our iron is our and then you have your cadmium. So those are 2 half reactions, yeah. So this guy's losing 2 electrons, and this one is gaining 2 electrons. So that's the number of electrons. Yeah, this is actually the number of electrons that are lost and then transferred, which is the same number. So it'd just be 2 in this case. Yes. Not according to the reaction. According to the reaction, cadmium is the reducing agent, right? But it is being oxidized, right? It's going from 0 to +2. No, the reducing agents are things that get oxidized, so they're always the anode. The oxidizing agent would actually be the thing being reduced, and those would be the cathode. Yeah. So remember, the agents are sort of opposite of their name. So the reducing agent is the guy that gets oxidized, and the oxidizing agent is got to get reduced. Yeah. Because I decided to use the equation where I subtracted. And because you're subtracting, that's the purpose of subtracting, is it will change the sign for you. If you want to change the sign, like we've been talking about, you need to add the numbers together. You should get the same value. Yeah. So that's the purpose of that equation with the subtract part of it in front of the anode, because it's always going to be the anode that needs to be flipped. So by subtracting the anode, it changes the sign for you if you don't want to do it yourself. Yeah. Other questions? Okay. So we'll clean up here a little bit. Hang on 1 sec here. We're to see something. Okay, so hopefully that'll be better. It's picking up echo like in my head here. All right. So we're putting in our numbers now that we're good. So once again, it is 2 electrons there, 2 moles of it. And then on the bottom there would be our Faraday's constant, 96,500 joule per volt per mole. And then we have our natural log, and we'll just use our number there, 0.016667. All right, so I'm just going to kind of clean up, I think, this part of it here. So I'm going to do natural log of 0.011, nope, 166667. I'm then going to times it by 8.314, times it by 298, divided by 2, and divided by 96,500. That is going to give me here, E is equal to minus 0.04 volts minus a minus 0.05256 volts. By the way, Kelvin cancels, moles cancel, joules cancel, And the rest of it cancels here, and we end up with volts basically at this point. And we would then take minus 0.040 minus our answer, and that gives us 0.013 volts in this case, give or take with some rounding. Yeah. First off, any questions on that there? Is this reaction spontaneous? It is, barely. You got a little bit of positive voltage. If you blink your eye, it'll probably go away. But I guess technically speaking, we now have been able to achieve some positive voltage, which means technically if we calculate our delta G, that would hit us a -1, which means it should be spontaneous. So this is an example where you could obviously have a reaction that is non-spontaneous under standard conditions, which it was here. And again, by playing with something like here, we did the concentrations, you're able to sort of turn a non-spontaneous reaction into a spontaneous reaction because of the difference in the concentrations. Any questions on that? Yeah. How did I find out it was? How did I know it was non-standard conditions? It really was the concentrations there. So remember that under standard conditions, that basically means that, and those are pretty much all those values you find in the table, like the SRP table and so forth. But that basically means under standard conditions, which usually is accompanied by that little knot that you see over things like G's and H's and E's and stuff like that. That basically means that the temperature is 25 degrees Celsius. If there's anything to do with solutions, the molarity should be 1 molar. And if it's anything to do with gases, the pressure should be 1 atmosphere. So if any of those things are sort of not those things, then you're sort of under the non-standard conditions things. Very similar to the delta G one that we saw, where we had the delta G equals delta G naught, plus RT natural log of. Natural log of Q that we saw in the previous one. Again, here in this equation, same idea. Something was not under standard conditions. So, you would use that guy. Other questions on that? Yeah. We can use the value of G to represent if the reaction is spontaneous. So unlike S that we talked about, entropy, where you have to sort of calculate the delta S of the universe, right, to make that determination of whether or not the reaction is spontaneous or not. We could use basically the value of delta G, if it's positive or negative, by itself to determine if the reaction is going to be spontaneous or not, or basically head towards products or reactions based on sort of that answer. Yeah, because G is gives free energy, which means there's free energy available to do some type of work, which means in a negative situation, it would be given off that energy to do some type of work, which means probably a spontaneous process going to occur to kind of release some of that energy to go off and do some type of work. Yeah, so there's, in terms of E, that involves E, is that what we're talking about? Yeah, so there's the delta G is equal to minus NFE, then the Nearst equation that has it in there, and then there's also the one that has the equilibrium constant. Yeah, so the best rule of thumb is to, like we normally talk about, is sort of based on the information given to you. So if there's something that mentions equilibrium constant, like you need to find it, or they give you an equilibrium constant, then you probably should roll with the one that obviously has K. If there's no mention of that, but you're given like concentrations or pressures or something like that, then you're probably going to Nearst it up. And if you're just kind of given, just some SRP values, you'll probably use that delta G minus NFE, so it's really sort of based on the information given to you is usually the best approach. Other questions? All right. All right, let's try another one here. For the following, balance the redox reaction and calculate the E and K. So by balancing, I mean just basic balancing. You don't have to add waters or anything like that. So just, add some electrons if you need, all that kind of stuff. What's that? Yeah, so balancing the equation just means, just put these two together, make sure they have the right number of electrons before you add them together. So should probably give you what's above there, I think. Maybe yes, or maybe not. Okay, let's take a look. So in this case, we are looking for E and K. So again, if you just invested in remembering the Nearst equation, once again, when you do get to equilibrium, as I mentioned before, E will equal 0, Q will equal K. So you basically can get our equation that you need by basically just subtracting that whole thing to the other side. Gives you E naught is equal to RT NF natural log of K. And that is again why there's no negative on that other equation that we used before. At this point, we do want to find a couple of things here. We want to figure out which one is our anode and our cathode. And in this case, our cathode is it is the S406, I believe, in this case. And the chromium here, if you were scared of this one, you could have went to this one and looked, and this would be +2, right? And +3, which means really the chromium here is starting here and going in the more positive direction. So it's becoming oxidized. And that would have been all you needed, right? To know that this guy is being reduced. For the fun of it, the oxidation state of the sulfur on the left is what? That's a -2, yeah, which is a -12. We do need to equal -2. There's 4 of them, which means it's actually 2.5 would be the oxidation state there. This is -2, gives you a -6 equals -2. That would be a plus. What we got there? There's 2 of them, so it would actually be +2 in this case. So it is the sulfur that is starting at 2.5 and going to 2, which is a movement in that direction, which is being reduced. Remember, oxidation states don't necessarily have to be whole numbers. They can be like halves and stuff like that as well. Any questions on that? So that means, again, here, this would be our cathode. That would be our anode. That means to write this balanced equation properly here, we would take our top equation the way it is, since it's already a reduction reaction. Our E naught will be 0.17 volts. We will flip this second one. In addition to flipping the second one, I need to multiply it by 2. Yeah, so 2 gives us 2 of these and 2 electrons. And that's really why I need to multiply it by 2, right? To get the electrons the same. Now to go back to your earlier question, because I actually writing the equation and I flipped it, the E value here should then become positive 0.50 volts for that equation, right? The way it's written there, which means if I'm going to calculate E of the cell at this case, and I'm going to use those 2 numbers, I should add them together, right? And again, if you want to subtract them, you should use the original numbers without changing the sign. Again, is your call, whichever way you want to do that. So while I got them here, I will do the adding version here because I already flipped the sign of the anode. So my E of the cell will be 0.17 volts plus my flipped sign for my anode gives me 0.67 volts. First off, I guess that would be one of the answers we were looking for, actually. So that is the E of the cell right there. Once again, you would get the same answer if you took E of the cell is equal to my cathode minus my anode without flipping the sign. Once again, that's going to flip the sign for you, and you'll get down there as well. Any question on that there? All right, so we also want to get to this guy. So we can see from our equation, it is 2 for N. So N is going to equal 2. We have our temperature, and I think that is all we need. So maybe, nope. We will go here. So we're going to go with our E naught is equal to RT NF natural log of K. And we just had our E of our cell, 0.67 volts. We know our N is equal to 2. And our temperature converting to Kelvin there going to give us a 298. And I believe that is all we need, as our, obviously our R and our F is still constants at this point. All right, so we're putting it in here. 0.67 equals 8.314, 298, 2, and 96,500, and our natural log of K. So we can clean up this side here. We will get 8.314 times 298 divided by 2 divided by 96,500 gets us 0.67 equals 0.012837 natural log of K. We're going to bring that to the other side. Going to give us a 52.19. 2 equals the natural log of K. At this point, we will E both sides to get rid of the natural log. Obviously, when we do that, that just becomes K, and little E action there. Going to give us 4.6 times 10 to the 22 in terms of our equilibrium constant. Any questions on any of that? Again, with the E move and all that, depending on where you rounded, you might get a slightly different answer for the front part, but the exponent part should be pretty much the same. Again, especially with the rounding. I didn't round too much on my calculator, so I have a slightly different number there. Any questions on that there? So, yeah. You don't. So that's one of the things. If your question is when we multiply the half reaction by the number of electrons to get to the right number, it actually does not affect the E value. So you can multiply by as many as you want. It will have no effect on the SRP value that you see in the table. So that's one unusual thing, unlike like delta H or things like that, where you would affect it. It will have no effect on it. Other questions? So once again, we can kind of see if everything makes sense. I have an E that is positive, which means if I did calculate delta G, it should be what type of sign? Not everybody at once, but what type of sign? It should be negative. Yes, that would imply a like spontaneous reaction and heading towards the products. So if I'm heading towards the products, I should have a large value of K. I think that would qualify. Yes. So again, all those things should agree with each other, right? When you analyze your results there, right? Provided you analyze your results. If you don't, then just get the number at the end, I suppose. Any questions on how to calculate K, E, G, and any other letter in the alphabet? Okay, so we will then talk a little bit about batteries here. You just need sort of the general idea of batteries. I'm not going to ask you any specifically, like, tell me about a Duracell battery or anything like that, but maybe the Energizer and the Energizer Bunny, really not. But you need a general idea as we go through this of sort of how batteries are similar and a little bit different, obviously, than a traditional galvanic cell. But a battery is really just a galvanic cell or a series of combined galvanic cells that can be used as a direct electrical current at a constant voltage. They're self-contained. They have no salt bridge. They also have no beakers or sloshing solutions usually, right? So it's all sort of a built-in one sort of system, but it really is still a galvanic cell. And as we talked about, if you look in your battery compartment, right, there's usually a positive, negative sort of side, right? Depending on, know how you put your battery in. There's usually some wiring in there as well, which means as the process sort of happens, we get the electrons going out through the circuit there, right? As it goes out there, it turns on your equipment unless it's dead, but then it turns it on. And obviously this is basically a galvanic sort of cell that's happening within, the battery there, sort of taking care of it. So we're going to see a few different types of batteries. This is the first one, which is sometimes referred to as a dry cell. And it's I'm going to say Duracell in that case. Looks like the copper top there. It has an anode, which is a zinc can or container that's in contact with MnO2 and an electrolyte. It has this sort of carbon rod in the middle there that is also in the electrolyte. So electrolytes, right, are things that help conduct electricity, right? So that's why we have those electrolytes here. It keeps kind of like the salt bridge, everything flowing and all that good stuff. We got our positive side, right, where electrons would be attracted to, and our negative side where they would obviously be directed away in that case. These type of batteries, regardless of sort of the size of them, I'll give basically a 1.5 voltage, whether you have C batteries, AAA batteries, AA batteries, they all pretty much give in the same type of voltage. So really this guy here is sort of acting as like the salt bridge and kind of keeping both sides together. We see our zinc going from 0 to +2, which means it's being oxidized. And in this particular case, we do see we got our, for example, our Mn, which is +4 in this case, and our Mn on this side, which is +3, which is being reduced as it goes through there. And the electrons sort of travel through that process through the cathode, which is sort of the carbon rod that's in the middle there. This is the overall reaction that takes place. And once again, you do not need to memorize any of these sort of equations or anything like that. Another type of battery is a mercury battery. And a mercury battery is used extensively in medicine and electronic devices. It's a little bit more expensive. It has a stainless steel container, but it still has a zinc anode, which again is where oxidation will occur. It's in contact with a really strong alkaline. Alkaline means basic. So that is a base there, like KOH, as we see in this picture here, which obviously is a strong base. There's no change in the electrolyte composition during operation. The overall cell reaction involves only solid substances. That is one of the things that make batteries sort of long lasting, is like you don't kind of lose things along the way. So you got kind of solids on both sides. There's also something that makes things in batteries, as we'll see, kind of like rechargeable, is having those solid sort of guys on both sides of the reaction when you do it. Gives a little less of a voltage, 1.35, has a longer life, because you sort of don't see a lot of breaking down of the components as it is running, so it'll go for a very long time. A lead storage battery, which is basically your car battery, right? It's basically 6 cells that are joined together. Has a lead anode and a cathode made of lead dioxide. Both the anode and cathode are immersed in a sulfuric acid, usually as the electrolyte, which is why they call it battery acid, right? And all that good stuff. Under normal conditions, each one will give you basically 2 volts. So you got 6 of them, it's a 12-volt battery. And that's enough to power basically the ignition circuit and all the electricity in your car, unless you are running late and your battery is dead when you turn it on. It's always that day, like, oh, crap. All right. Also, why they are rechargeable and they don't go out, why we also have alternators in our cars, right, to alternate currents and all that good stuff, to make it rechargeable. Otherwise the battery would just sort of drain out and die. You could check for the healthy battery by checking its density, and a good battery has 1.2 grams per milliliter of the electrolyte that's in there. In cold weather, sometimes the electrolyte gets a little bit more viscous, which makes it a little bit harder to sort of turn on, a little less power. Things aren't flowing as well in really cold weather, which luckily we don't have to worry too much about here. Here's a cross section of your battery in your car, which nowadays, a lot of times the battery itself is not actually in the engine. A lot of times it's in the trunk or under the back seat. Or if your car is electric, you got a lot more batteries under there, and the different type of batteries. But we do have our cell here, our anode and our cathode. If you ever jump the car, right, it's always the question of which color goes on which. Try one and hope I don't get fried, right? And try the other one and all that. So a lot of times, like I said, you don't actually have the battery. You just have like even you have like a cable in the front of your engine a lot of times these days. But these series of cells, if you put them in a row, will sort of increase your voltage. Usually our batteries are sealed these days, so you can't get in there. But we do see a lot of what we just talked about, sort of solid on both sides of the equation, which is why, you know, the batteries do last a very long time. They're able to sort of recharge themselves because kind of the reversible reaction is able to be happen because you have solid basically there on both sides. But here we do see our lead go from 0 to a +2 situation, and is being oxidized in this case. And we do see the sulfur, the lead over here changing from +4 over here to +2. So it's being reduced in this case as it goes to the other side. Another type of battery is a lithium battery. It has an anode that is a carbon containing sort of graphite, and it has holes that allows really the lithium guys to kind of migrate across the medium there through the electrolyte to the other side where the cathode is. It can be charged hundreds of times without deterioration. It's like our tools, right? You use drills and stuff like that, lithium batteries, because there's also a very light metal at 6.94. So it's really light, and you can recharge it a lot of times before you sort of lose the ability to do so. A fuel cell is another, not technically a battery, but does sort of operate very similar. In a fuel cell, this is a hydrogen fuel cell, which, you know, years ago, that's kind of what they wanted to make cars kind of run on. And that is because the overall reaction here is basically just the production of water. It has hydrogen being funneled in, oxygen being funneled in, and again, our anode and cathode reaction here, where our hydrogen goes from 0 to +1, and our oxygen goes from 0 to -2 and gets reduced in this case. Obviously, we've moved more to batteries and hybrid type cars than trying to do this, as we don't really have gas stations with hydrogen gas to fill up things. All right, so those are some batteries. Let's also talk a little bit about another aspect of redox reactions in life, which is corrosion. And corrosion is returning metals to their natural state. At one time, 1/5 of all sort of iron and steel production was used to replace rusted out metals. Any metal with an SRP value less positive than oxygen can go through corrosion. Why would that be? If you have a metal and you have oxygen, and this guy is less positive SRP, when these two guys get hooked up together in a redox reaction, or like a galvanic cell, which one would be the cathode? Oxygen would be the cathode. The metal would be the anode, where oxidation occurs, and that is basically corrosion. Yeah, so basically the oxidation of those metals will corrode, and it will be spontaneous as well, right? In that process, when you do that, and it will cause corrosion to occur. Most metals, though, not necessarily all corrosion is necessarily bad. A lot of metals will actually form a thin layer of protection Even though the sort of top layer goes through corrosion, it actually will be able to kind of protect the rest of the metal that's underneath it. So aluminum is an example of that. Aluminum will form sort of a little layer that will actually protect, the rest of the metal that's underneath there, this layer, once it kind of goes through corrosion. The bad thing, though, about, say, iron and rust is iron does the same thing, but that little shield falls off. And then that exposes fresh metal to go through corrosion that will then fall off. Before you know it, you have a big old corroded, rusted out hole in your piece of metal. So sometimes it can be protective. And in the case of rust and iron, it is not protective. A copper forms that sort of patina color that we see, which is greenish carbonate color. And that some people pay a lot of money to get that sort of patina type color on things. Silver will tarnish, and gold, which has an SRP value of 1.5, has no corrosion pretty much in air. And that is because in the case of gold and oxygen, gold at 1.5 volts has an SRP value more positive than oxygen. That means when gold and oxygen gets hooked up, the cathode is the gold. And the anode, where all the oxidation and bad things happen, is the oxygen. And that's why gold will not go through much corrosion that occurs in this case. Any questions on that there? So basically, to make rust, which is iron 3 oxide, you basically just need a few things. You need iron, you need a little bit of oxygen, and some moisture, pretty much. So steel has a lot of non-uniform parts, and that allows really the oxidation of iron to occur. It actually occurs in sort of 2 steps. You first make iron 2, and then it gets further oxidized through the process to iron 3, where eventually we'll make iron 3 oxide, which is what we sort of commonly call rust in this case. And here's a picture of that. Again, our iron 2 going to iron 3. You have these non-uniform points where really moisture just from the environment can kind of sit there in those holes, along with our air, which would provide the oxygen. And then we get all of our rust that can form in this case, costing lots of money. There are a couple of ways to prevent corrosion. So let's talk a few ways of preventing it. So when you get that question, you answer it. You can apply paint or metal plating to your metal. Hence, they sell a whole line known as Rust-Oleum paint, right? To prevent rusting and all that good stuff. Chromium and tin can be used to plate it. So you could add some type of coating to your metal, which again will provide a protection for the metal that's underneath it. Galvanizing is an example of that. Zinc is more active metal than iron. So when we look and we put zinc and our iron together, zinc at minus 0.76 and our iron at minus 0.44 SRP, the iron is more positive, which means in this case, our iron would then become our cathode. The zinc will become our anode. So all the bad oxidation will happen at the zinc. Hopefully will protect the iron that's there as well. So as it says there, zinc acts as a sacrificial sort of coating. Another way is you could do some alloying. You could add other elements that will change the SRP value of that metal to somewhere where it will kind of become like gold and a noble sort of metal, where no effective corrosion will occur. You could also have cathodic protection. So for example, if you take magnesium that's connected to a wire in a tank that's buried underneath the ground, for example, magnesium is a better reducing agent than iron. And if you're a reducing agent, that means what is happening to it? It is being oxidized, which means it's going to be our anode. And again, in this case, the magnesium will take the brunt of the oxidation and corrosion, again, protecting the iron in this tank. So obviously, if you buried a iron tank underground, there's a lot of moisture in the ground. And without sort of the magnesium here, taking off all the oxidation this tank would go through oxidation and probably spring a leak, right? Which is why you used to see years ago at gas stations, every so often they would be digging up the ground underneath there. Any questions on corrosion? So batteries, you need to know how they're similar to galvanic cell, how they're obviously a little bit different. You need to know what corrosion is. You need to know a couple of ways to protect against corrosion. Any questions on any of that there? All right, so we're going to finish up here talking about electrolysis. Electrolysis is the process where electrical energy is used to really make a non-spontaneous process occur. So for example, if we take sodium chloride, it is not spontaneous to be able to get back the elements, right? We don't usually get the sodium metal and the chlorine gas coming back at us. Otherwise, our French fries would not taste so great coming out when they put salt on them. So under normal conditions, right, that's not a spontaneous process, basically to break these guys back down into their elements. So applying an electrical current or some other source of maybe some pressure, but really running some electrical current is a way in which you can basically break these guys back down into their natural states. So by applying a battery here, we have our anode, which goes to our cathode. So let's talk a little bit about putting together sodium chloride. I'm going to erase this. So when we put together sort of sodium chloride, we have sodium plus some chlorine making sodium chloride. That means the sodium here, right, is going from 0 to +1, and the chlorine is going from 0 to -1 when we actually produce sodium chloride. In this case, the guy that is being oxidized is which one? It is the sodium, and the one that is being reduced is the chlorine, right? Which means that that would be our cathode, and this would be our anode. In the case of electrolysis, we're actually starting with the sodium chloride, which means we're starting with the sodium chloride, and we're going to make, obviously I didn't balance any of these equations, but we'll just look at the elements. And we're going to actually make these guys, which means when we go through electrolysis, the sodium starts at +1 and ends at 0. And the chlorine starts at -1 and ends at 0. In this case, through electrolysis, what is being oxidized? It is the chlorine here, while what is being reduced is the sodium, right? So it's actually, I'm sorry, it's actually the Cl- is really the right one there. Cl-. So that's why when we look at the electrolysis setup here on our anode side, it is actually the chlorine, because we're taking the chlorine in this case from -1 back to its natural state of 0. And our anode, our cathode is actually going to be the sodium ion going back to sort of solid sodium. So in electrolysis, because we're really making kind of like the reverse reaction occur, our anode and our cathode are opposite of what it would be if we were making the substance. So breaking it back down will be opposite anode and cathode. Any questions on that there? Okay. So that's something to keep in mind, because sometimes when people go through electrolysis problems, they think about it like this, which would then put your anode and cathode on the wrong side for your electrolysis cell. So you're actually going the opposite way when you do it. This is the electrolysis of water, which maybe you did in an experiment along the way. They don't let you do that here, I don't think. Well, you pretty much just need some acidic water and a 9-volt battery and some electrodes, and you can do it. And when you do it, we are again going in the opposite direction here. We are taking water and we're making hydrogen gas and oxygen gas in this case. So again, it's going from +1 and -2 to 0 and 0 in this case. So as you run a battery through it, you will break apart the water. You do need usually to make just a little bit acidic, the water, to kind of help the process along, add a little extra hydrogens to make it a little bit more efficient. And then you can collect it, as you see here in this picture, in some tubes. And in these empty spaces, they're not really empty. That is where the gas is, right? So the gas is in these empty spaces here. That's your hydrogen gas and your oxygen gas that you collected. Why is there more hydrogen than oxygen? Yeah, it's H2O, yeah? So twice as much hydrogen to oxygen. So that's why you see twice as much there collected of hydrogen versus oxygen when you do it, and it breaks back down into sort of elemental form. By the way, when you're doing electrolysis problems for water, they oftentimes will not tell you, hey, we're doing the electrolysis of water. As I mentioned before, oftentimes we'll make this more acidic. So they'll mention something like an acid, like you added some sulfuric acid, running electrolysis of sulfuric acid. That is pretty much electrolysis of water in book problems. So again, a lot of times they won't come straight out and say you're doing water. They'll just talk about, doing something with maybe sulfuric acid. That would mean that these would be our half reactions that we would want to use in our calculations. So we're going to talk about calculations here and electrolysis problems, and they have a fairly straightforward sort of setup as to how you go about doing it. So typically you're given the current and an amperage, and an amp is equal to a coulomb divided by a second. A coulomb is a unit of electrical charge, and a second obviously is time. They will also give you how long you run the cell for, how long in time you run the cell for. So typically what we want to do is take our time and convert it into seconds, because then we can take the seconds times the amperage, which is a coulomb per second. The seconds will cancel, and that will give you basically the coulomb of charge associated with your cell. We then will typically use this guy, which is our Faraday's constant, basically. We'll use Faraday's constant in a conversion to go from 96,500 coulombs to a mole of electrons. This will end us with a mole of electrons. It is at this point where our half reactions come into play. So we would go to our half reactions and do moles of electrons to moles of whatever you are interested in, be it hydrogen gas, oxygen gas, metal, silver, whatever it may be. At some point when you do this calculation, you will be left with moles of something. And then you may have to figure out how many grams, which would be the molar mass, right, to do that. But if we do have a gas like hydrogen or oxygen gas, a lot of times when we're figuring out gases, we're not interested in grams, but we're interested in volume. So a throwback Thursday, PV equals nRT is sometimes used in these problems for gases. That is what? That it is, right? That means the pressure should be in what unit? ATM, right? Volume should be in liters. Moles should be moles. Temperature should be Kelvin. And the gas constant here is the 0.08206 version, right? Or 0.0821 if you like that number better, yeah. So sometimes you may have to put the moles into the ideal gas law and solve for volume to figure out how much volume of a gas you would collect. So very common, like in the water example there, we would probably be interested in the volume of hydrogen and the volume of oxygen that we collected as this cell ran. Opposite of this would be they tell you how much you produced of something, and you run backwards and figure out maybe what amperage you were running the cell at or how long you ran the cell. So kind of back and forth is the very typical sort of calculations. Any questions on that? So let's take a look at one here together. We'll come back to this one. Let's do this one first. So we want to know in this case how many grams we'll go with. of calcium would be produced in this cell if we ran it at a current of 0.45 amperage for 1.5 hours. So what we're going to do is, in this case, for calcium chloride, we're going to start with calcium chloride just to give you an idea here. We're going to have calcium plus a couple of chlorides. And in this particular case, we have this guy and this guy going back to their solid states and their gas states. So this guy would come back to calcium and this guy would come back to chlorine. So what is happening here is the calcium is going from +2 to 0, which means it is being reduced, which is why it is the cathode in this case. The chloride is going from -1 to 0, which means it's becoming more positive, which is why it is the anode in this case. So again, it is a little bit backwards. So to start this, we're really just going to start it like normal. We're going to take our 1.5 hours and we're going to convert it into seconds. So in 1 hour, there's like 3,600 seconds, give or take a second or two. Gives us 5,400 seconds. The reason I did that is my amperage is 0.452 amps, which is 0.452 coulombs per second. So using that as my next conversion, 0.452 coulombs per second. The seconds here will cancel out and we will end up with this cell, because it ran that long, will give us something like 22,440.8 coulombs. Now we're going to use Faraday's constant. Our 96,500 coulombs is a mole of electrons. So we're going to take that and divide it by 96,500. Gives us 0.0253 moles of electrons. So this is basically our time times our amperage. This is converting our charge into moles of electron. Any question up there? Now, in this case, we're interested in calcium. So we would go to the balance half reaction and we see for every 2 moles of electrons, we get 1 mole of calcium. So that is how we're going to get to calcium in this case. Basically like stoichiometry. Moles of electrons will cancel. We'll times it by 2. .051 moles of calcium. And at this point, if I wanted to know how many grams that would be, I would go to the periodic table, look up calcium, 4008, I think. What's that? We would want to divide by 2. I multiplied, which is clearly not right. Just want to make sure you're awake. We'll just cut that out of the video later. All right, so that's probably maybe a better number if you actually do the correct math there. There we go. So you're telling me I should divide, which I probably agree with you on that. 127. I know, I'm free to do whatever I want. I know, it's okay. That is moles of calcium. All right, so now I'm going to times that by 4008. I'm timesing at this point, right? See, I told you the 0.5 would be here at some point. 0.5, 1 or 0.51 grams of calcium would be produced. I was just like ahead of the game. That's what I wanted to say there. Or I just screwed up royally. It's probably that one. All right. So what this basically means, obviously, is if we ran this cell for 1.5 hours at this amperage, we would expect to get out there about 0.5 gram of calcium. We could also, if we wanted to, right, figure out the chlorine in this case by just really starting here and using chlorines, mole to electron to mole ratio, which in the case of chlorine would also be 2 moles of electron for 1 mole of Cl2, which could give you your moles of chlorine, which again, probably you might want, maybe not to know the grams, but maybe you'd have some other information. You could use the ideal gas law or also figure out grams if you wanted to as well. Any questions on that? All right, so why don't you try one and do a better job than I did here? Let's do the one we skipped, which is the electrolysis of water. So we're going to run it for 1.26. It's passed through a cell that contains sulfuric acid. So this is what I was talking about earlier. They don't really mention it as being water, but that sulfuric acid tells you it's water. For 7.44 hours at STP. STP is standard temperature and pressure. Yeah. Pressure is 1 atmosphere. Temperature is 273, right? So that's what STP stands for. Okay, so since we're getting to the end, why don't you finish up that and we will